Hello ladies and gentlemen. Now I will presenting about investigation the effect of stator slotting technique and shaping magnetic on the performance of permanent magnet machine. The author is Lisa Evelyn, Tajudin Nur, and Marsur Siregar. Presenter is me, Lisa Evelyn. Next is paper outline. 1 is about introduction, 2 analysis and simulation result using FEM, 3 normal and tangential flux density of permanent magnet generator, 4 computation cogging torque reduction of the PMG, 5 conclusion. The introduction in renewable energy systems such as a wind, water, tidal wave, and so on, the utilization of special electrical machines such as permanent magnet generator or PMG is one of the most important parts in order to harvest the electric energy. The reason is that the PMG has some advantage over the other type of electrical machines such as high efficiency, lower maintenance, and high power density. However, the most issues related to the PMG application in water power system is the cogging torque or CT. The cogging torque in PMG produce active force between magnet in rotor and stator core. The presence of the CT in the PMG lead to reduce the ability of the blade to be rotated, particularly in lower water speed condition. The effect of stator slotting technique and breadth of flow magnet structure on permanent magnet machine performance was investigated in this study. For purpose of study, a fractional slot number of 24 slot and 1/8 pole has been selected. The permanent magnet machine studied in the paper are inner prototype with radially flux distribution. 3 different structures of permanent magnet machine was analyzed based on numeric, and the results regarding their performance were compared. It was being focused on surveying the magnetic flux distribution in air gap of the machine studied. The analyzed result of permanent magnet machine studied was validated by employing the finite element method magnetic software, or we call FEM 4.2. And this is 3 different picture of machine, the structure of PMG studied. A is reference the initial structure, which refers to the conventional structure of PMG. In figure B, the magnet structure is shaped in the edge in order to achieve density reduction. The 2 dummy slotting in stator seats was employed. The presence of 2 dummy slotting in stator core affect the increase the point contact between magnet surface and stator seat. This lead to increase the CT frequency and reduce the CT peak value. The CT value of the PMG can be reduced effectively, but the CT reduction is still not sufficient for renewable energy system purpose. For conduction, the task in figure C, 3 dummy slotting stator core has been applied. Next is analysis and simulation result using FEM. Relation between tangential flux density and CT can be shown in equation. This one, we have BT. BT is normal flux density. Bn is normal flux density. Bt is tangential flux density. One can observe the tangential force affect the tangential flux density affect to the value of the CT. Thus, for reducing CT in any PMG, the tangential flux density must be minimized. It has been understood that the location of the tangential flux density is around the magnet edge. So, by performing shaping in magnet edge could reduce the tangential flux of the magnet effectively. However, the effectiveness of shaping in magnet edge, it depends on the type of machine. For example, in fractional slot number, as studied in this paper, the CT conduction may be easier compared with the integral slot number. In this paper, the normal and tangential flux density for PMG studied and analyzed and presented. This is the normal and tangential flux density of PMG. We have three different pictures and we have three different type magnetic flux density. One, magnetic flux density of initial structure. B, magnetic flux density of magnet edge shaping with two dummies floating in stator core. 3. Magnetic flux density of magnet edge shaping with 3 dummies floating in stator core. This is normal flux density of magnetic flux density of initial structure, or BN. This is magnetic flux density of initial structure, tangential flux density, or BT. This is normal flux density of magnetic flux density of magnet edge shaping with two dummies floating in stator core, or BN. This is picture about tangential flux density of magnetic flux density of magnet edge shaping with two dummies floating in stator core, or BT. This is normal flux density or BN in magnetic flux density of magnet edge shaping with three dummies floating in stator core. This is BT, tangential flux density of magnetic flux density of magnet edge shaping with three dummies floating in stator core. From 6 picture, the tangential of PMG with shaping and dummy floating is lower compared with initial structure. It can be observed that tangential flux density of magnet edge shaping with the 3 dummies floating in stator sheath has the lowest of tangential flux density among the PMG studied. The tangential flux density a great influence on the CT peak value. This is computing cogging torque reduce of the PMG. Cogging torque compare the PMG or PMM studied. As the CT of the PMG reduced significantly, lead the performance of the PMG become increased. Using the FEM 4.2, the CT of the 3 dummy floating and 2 dummy floating is computed, and it has been found around 98.73% and 84.66% representatively. The comparison of the CT peak value of 3 PMG studied is presented in this picture. The blue or A is the initial structure. The black color, or B, it's the using 2 dummy slot in stator core. C, the red line, is the using 3 dummy slotting in Stator core. Based on figure 5 or on this figure, one can observe the CT reduction of the PMG is affected by the tangential flux density in air gap. As can be seen for this picture, the CT of the PMG with magnet shaping and dummy slotting tend to reduce. The red line in graph represented the magnet edge shaping combination with 3 dummy slotting in Stator seat, which has the highest of CT reduction compared among the PMG studied. Since the CT of the proposed PMG become decreased, it could increase the performance of the machine. In addition, another benefit of employing the shaping magnet combination with 3 dummy slotting in Stator seat is the fact the magnet flux density in Stator and rotor core also become decline. Lead the eddy current losses also become smaller compared with the initial structure. And this one conclusion, it has been found that the structure of 3 dummy slotting in Stator core combined with magnet edge shaping in rotor core could reduce the peak of cogging torque significantly of the proposed permanent magnet machine around 98% compared with the initial structure. The combination of PMG edge shaping and 3 dummy slotting in Stator core could be implemented to reduce the CT of the proposed PMG. Thank you for the attention.